Hello, my dear student friends. Welcome back to our channel, Get Instrumentation Engineering. Today, we are going to discuss about the system stability, okay, control system stability. So, the system stability is the one of the most performance specification of a control system. A system considered to be as unstable if it does not return to its initial position, but continue to oscillate after it is subjected to any change in input or it is subjected to a undesirable disturbance. Okay, for any time invariant control system to be stable, it permits to the following conditions. Okay, it should satisfy the following conditions. What is the condition? The system will produce a bounded output for a bounded input, right? Bounded input, bounded output. So stability called BIBO. Okay, bounded input, bounded output system. Understand? So if there is no input, the output output should tend to zero. Okay, irrespective of any initial conditions. Understand that? So these are the two important conditions to be satisfied for a stable system. Clear? So the definitions there are actually, if you consider any system, okay, any system. So stability analysis, right? Stability. So the system response, there are two types of responses normally we call. One is a natural response and a driven response. So there are two types of response. Okay, so system response, two types. One is natural response. Okay, natural response. Another one is driven or forced response. Okay, driven response or called a forced response. Okay, we can define the categories of stability based on, we normally categorize the stability of any system based on natural response, right? Natural response of a system. Okay, so we normally categorize based on natural response. How do we classify? Stable, unstable, and marginally stable. So a system is said to be stable. Okay, first category is stable system. So we classify natural response based on natural response. What is a stable system? Is stable. Its natural response. It's okay. It's natural response zero. Okay, zero. The natural response becomes zero as t tends to infinity. That means a system is stable means if its natural response tends to zero as t tends to infinity. So when apply t equal to infinity, then it should give zero. Okay, second category is unstable. Okay, unstable. So what is a unstable? When the unstable is its natural same condition, when it is called unstable, its natural response tends to infinity as t tends to infinity. So when t tends to infinity, its natural response also tends to infinity. This is called unstable. Okay. Third is marginally stable. What is the natural response for marginally stable? So marginally stable. A system is marginally stable if its natural response neither decays or grows. Okay, understand or not? So a system said to be marginally stable, its natural response its natural response okay, neither decays or grows. Sustained, this is called a sustained oscillation. Grows, but remains constant, constant or oscillates. Okay, oscillates. So this is the natural response based on the natural response. Next is, as I told you, BIBO stability. Definition for stability. What is the definition for stability? BIBO stability. BIBO stability. Understand, my dear students? BIBO, bounded input, bounded output. Any system called to be a stable system, if its output of the system is bounded for any bounded input. Okay, so output is bounded for any bounded input. Okay, any bounded input. Okay, any signal is called bounded if the maximum and minimum value are finite. Okay, any signal is called bounded. Okay, bounded. Understand or not? Any signal is called bounded if the maximum and minimum. Okay, maximum and minimum. Clear? So minimum value are finite. Okay, finite. Clear or not? So a system, this is a system, input is bounded, output is also bounded. Okay, so bounded input, bounded output. It's a system. Understand? So the stable system is every bounded input yields a bounded output. Understand or not? If it is not yields the output, if the system is unstable, the bounded there is not a bounded output for the input case, right? For example, let's see some example for bounded input and bounded output. Say example, this is say so this is say this response is exponential to the minus t. Okay, e power minus t u of t. Okay, this is, say this is 1. Okay, 1, maximum value 1. This is an example for bounded. Okay, bounded input and bounded. That is, this is a stable system. Okay, so this is a stable system. So you can have one more example. This is unbounded. Okay, say this is positive e exponential, remember? So positive exponential, positive e of t, u of t. So when it is unbounded, this is example for unbounded. Say consider a ramp input. So the ramp response. Okay, so this is a ramp 0. This is also unbounded. Ramp is an example for unbounded. So ramp. Another, see sinusoidal. Okay, sinusoidal signal with the progressively increasing. Say starting from this like this. So this response, this is not bounded, sinusoidal. This is called not bounded. Understand? See, exponential is positive, then it is unstable. Exponential is positive and stable. If we have exponential is negative, this is is stable. Exponential negative means stable. So basically see the stability, basically the stability of the system, stability of any system depends on only the location of poles. The stability of any system depends on the location of poles, not on the location of zeros. Understand? So in the transfer function, denominator roots are called poles, numerator roots are called zeros. So the stability never depend on the zeros of location of zeros. So the stability of any system depends on the location. Don't forget location of poles. Okay, not on the location of zeros. Understand, my dear student friends? Only zeros. So another conditions. Okay, this is one condition. Another condition: if poles are located in the left side of the S plane, say this is S plane, real minus real, imaginary minus imaginary. Okay, this is imaginary axis, this is real axis. Okay, if the poles are located in the left half of S plane, okay, if the poles are located in the LHS of left hand side of the S plane, then the system is stable. Next is the impulse response. We can also classify based on impulse response. The impulse response of a casual and stable system must be absolutely integrable between the limits between 0 and infinity. So the impulse response, the impulse response of a causal and stable system must be integratable. System must be absolutely integrable. Okay, integrable between the limits. Okay, between the limits. What are the limits? From 0 to infinity. Between the limits from 0 to infinity. Say you can have 0 to infinity, impulse response d of t. So the impulse response of a causal and stable system must be integrable between 0 and infinity. Clear? So if the roots are located on the imaginary axis, okay, on the imaginary axis, which are repeated, the system is unstable. This is one important. If the roots are located on imaginary axis, okay, also repeated, then the system is unstable. If the roots are located on the imaginary axis IA, okay, which is repeated, the roots are repeated and located on the imaginary axis and repeated repeated, then the system is unstable. Clear? Unstable. Okay, in that case, so here the system equal to infinity. Okay, not equal to infinity. The system is casual and right, not infinity. Here the system integral of 0 to infinity impulse response d of t equal to infinity because unstable. If one or more poles are located on the right half of the S-plane, the system is unstable. If one or more poles located on the right half of the S-plane, okay, so the system is unstable. If one or more roots located roots or poles, okay, poles located on the RHS of this plane, RH of this plane, then the system is unstable. The system is unstable. What is the condition for unstable? Integral of 0 to infinity impulse response d of t equal to infinity. Okay, 0 to infinity, that is infinity. Say as poles approaches origin, stability decreases. Another important point, as the poles approaches, as a pole or any poles, okay, pole or poles approaches origin, okay, approaches to origin, okay, the stability decreases. Stability decreases as it approaches to origin. Say this is a pole. As a pole approaches towards the origin. So the stability decreases. When non-repeated or simple poles are located on the imaginary axis, when non-repeated, okay, non-repeated or simple poles are located on the imaginary axis, okay, then the system is marginally stable. Suppose an ordinary pole located on the imaginary axis, a simple pole on the imaginary axis, okay, so it is called imaginary axis. Then the system is okay, then the system is marginally stable or limitedly, so it is called marginally stable, okay, marginally or limitedly, okay, limitedly, or also called critically, so critically damp, okay, critically, or just stable, or just stable when t tends to infinity. So impulse response, okay, so in this case impulse response neither approaches to 0 or, okay, or goes to infinity, okay, and will have a fixed impulse response and have infinity and have okay, understand or not? Fixed impulse response, Let's see some of the approaches. This is first column is transfer function. Let's see that. Let me change the color. Say this is a transfer function of system, typical transfer function. This is impulse response. Okay, so this is impulse response of a system. This is pole location. Okay, pole location on S plane. Pole location on S plane. Okay. So this is about stability. Stability. This last one is stability. So this is stability. So stability, right? So this is this transfer function for Laplace domain in transfer function for sinusoidal signal sin omega t. So Laplace transform of sin omega t. This is impulse response is sinusoidal. So the location on the two imaginary axis, two complex poles on the imaginary axis. So this is marginally stable. So this is stability condition is marginally stable or limitedly stable, just stable, right? Next, see the transfer function. So transfer function time domain is t into sin omega t. So 2 omega s divided by s square plus omega square the whole square. So this is the impulse response of the transfer function. So you see here it is tends to infinity, right? So what happened to here? There are two or more imaginary poles, complex poles on the repeated poles on the imaginary axis. The system is unstable. So you consider another time domain system 4 e power 2t u of t. So the transfer function for this time function, the system in time domain is 4 by s minus 2. So as I explained before, this is unbounded. So it's okay. This is unbounded. So there is a pole. See here the denominator, a pole at s equal to 2. So it lies on the right. One or more pole lie on the right half of the s plane, that becomes unstable. Okay, same criteria here. Consider the transfer function whose time function is e power minus 2t sin 3t u of t. Okay, so this is e power minus 2t sin 3t, whose transfer function is 3 by s square plus 4s plus 13. Okay, 13. So if you obtain the impulse response of the system, so it becomes like this, right? So it tends to settle. Okay, it tends to settle. So this system is when t tends to infinity, it becomes 0. Okay, 0. So then when t tends to infinity, when the impulse response 0, then it is stable. This is one condition. Another condition is if you calculate the poles of the transfer function s square plus 4s plus 13. So it has poles. Okay, so poles, complex poles, two complex pole, one real pole. Okay, actually two complex poles, 2 plus j3, 2 minus j3. Okay, 2 plus j3, 2 minus j3. So it lies on the left half of the S plane, then the system is stable. So another transfer function, just a step response. Okay, step input u of t. So whose transfer function is 1 by s. So 1 by s. So what is the 1 by s? This is the impulse response of step function. So it is on the when s equal to 0. So the pole at s equal to 0. So this is just stable or strictly stable. Okay, just stable. That is marginally stable or strictly stable. So then move to ramp. Say already we discussed, this is a ramp ramp input. So ramp input whose transfer function is 1 by s square. So there are two poles at the origin, repeated poles, 0 0 at the origin. So this is not bounded. Okay, not bounded. This is not bounded or unbounded. So the system is unstable. Clear, my dear students? Any doubt with this? Right. Next we go for, see here, you can simply from this expression you can easily tell me. So if this system has e power minus 2t. So the exponential term consists of negative term. So the system is stable. Okay. So the system is stable. So this system is stable. Whereas you go here, so exponential term, it contains plus, okay, positive. When exponential term consists positive, then the system is unstable. You can easily tell from the function or from the transfer function. You see the denominator is the denominator equation contains a negative term. So that also an indicator for instability. So this system has two plus, okay, 2 plus j omega, 2 minus j omega. It lies on the right half of the S plane. Okay, so this is also unstable since both pole lie on the right half of the S plane. So then you go here, you see here also you can find out the exponential to the power is negative. So obviously the impulse response settles when t tends to infinity, it becomes 0. So when t tends to infinity, this system becomes impulse response tends to 0. So this also stable because both poles are lie on the left half of the S plane. Understand? This is the concept of stability based on impulse response. Understand? Impulse response. Any doubt with this, my dear student friends? Okay. Good. Next, we can classify the stability. Okay, stability classification. Stability classification. How do you classify stability? Stability can be classified based on, there are two types of stability. So absolute stability, absolute stable system. So, stable system itself, okay, can classify absolute stable system. Then unstable system, then conditionally stable system, conditionally stable system. Understand? When the gain parameter k is varied from 0 to infinity, when the gain parameter k increase from 0 to infinity, okay, if the poles are located on the left half of the S plane, this infinity, if poles are located in the left half of the S plane, okay, it is when we vary the gain from 0 to infinity, and if the poles are located on the left half of the S plane, okay, it is always absolutely stable. So this is called absolutely stable condition. Understand? If the system is stable only for limited values of gain, okay, if the system, understand or not, system is stable only for limited values of k, please remember, if the system is stable only for a limited value of gain k, okay, then it is called conditionally stable. conditionally stable. Understand or not? Okay. So these are all the cases of absolutely stable and the conditionally stable. Okay. Next is closed loop stability, closed loop pole stability. Next is, this is open loop poles. Next is closed loop pole stability, closed loop poles stability, poles and stability. How to classify stability based on closed loop pole? Understand? So a system, stable system for a closed loop, stable. So when it is stable, all the closed loop poles of a system lie on the S plane. All the poles, closed loop poles. That is the important point. All the closed loop poles lie on the left half of the S plane. Left half of the S plane. Clear? Say if it is not any, at least one pole on right half of the S plane or repeated poles on the imaginary axis, that is unstable. So when it is unstable, the closed loop poles at least, okay, at least, the word at least one pole, in the right half of the S plane, right half of the S plane, or repeated poles, or repeated poles on the imaginary axis. Understand? Then marginally stable for the closed loop poles. Marginally stable. When it is marginally stable, okay, the system has non-repeated poles on the imaginary axis. Non-repeated poles. Repeated poles on the imaginary axis. Okay, axis, or possibly poles in the left half of the S plane. Okay, poles in the possibly. Okay, and this is enough for you. Okay, poles in the left half of the S plane, or possibly poles. Okay, possibly few poles, in left half of the S plane. So this is condition for closed loop stability. Let us see some example. Consider a second order control system, say G1 of S, okay, equal to 15 divided by S plus 3, S plus 5, and G2, say there are two systems, G2 of S equal to 8 divided by S square plus 4S plus 8. S square plus 4S plus 8. So this system has the poles at S equal to -3 and -5. Okay. Whereas this system has poles S equal to -2 plus or minus J2. Okay. So the step response of this system, okay, step response of G1, okay, step response of G1, that is G1 equal to, what is step response of G1? Let's say C of t, okay, step response G of t or C of t, C1 of t equal to 1.5 e to the power -5t minus 2.5 e to the power -3t plus 1. Okay, so in this this is step response of C1 of t. So C2 of t equal to minus e to the power minus 2t. Okay, so cos of 2t plus sine 2t plus 1. So this is step response of G2. This is step response of G1. Okay. So how to differentiate the stability of the system? Okay. Both responses are superposition of natural response as well as the driven response. Okay. Both responses are both step responses are a superposition. Okay, superposition of natural response, that is transient, right? So both responses are having natural, that is transient, right? Natural response, that is the transient behavior, transient response. Okay. Also, both has a driven forced response. What is driven or forced response? Steady state response. Okay. So driven both step responses has driven or forced responses. Forced response, that is steady state response. Clear? Steady state response. So what is natural response? Say both if we subject it to infinity, if both in both cases you see in G1 of t you apply t tends to infinity. Okay, when t tends to infinity, e to the power here is -1. Say this is 1.5 minus 2.5 minus 1 plus 1 minus 1 plus 1. When t tends to infinity, c1 of t becomes 0. Similarly, you substitute here e to the power infinity minus 1 cos infinity sine infinity, both are 0, right? So c2 of t also 0. C2 of t also 0. So both, okay, both responses, so both system step responses are respond to driven as well as the natural response. So both has the steady state driven response values plus 1. Both has driven response plus 1. So this driven response also plus 1. This driven response also plus 1. Both are superposition, response to superposition of these two natural as well as driven response. Okay, let's see the response of the system. See, this is the response of both systems. Okay, so this is so since this is C1 of t, sorry, C2 of t, this is C1 of t. So since from this both systems are stable. Okay. So the next case, now consider another example. Okay. So G1 of S equal to 15 divided by S minus 3, S minus 5. Okay, similar system but with a different sign. Okay, then G2 of S equal to 8 divided by S square minus 4S plus 8. What are the roots of poles of this function? S equal to 3 and 5. What about here? S equal to 2 plus or minus J2. So these poles are lying on the right half of the S plane, then you can easily say the system is unstable. Okay, their step responses C1 say C1 of t for this system, since the poles are distinct and unequal, you see 1.5 e to the power 5t minus 2.5 e to the power 3t plus 1. So as I explained earlier, you look into the exponential power. See here, so positive. So obviously the system is unstable. Whereas you see here, the exponential power is negative. Obviously the system will be stable. Okay. Here also you can see, you can look into here. Okay. So the system, similarly, the step response for C2 of t equal to e to the power 2t, okay, minus e to the power 2t cos 2t plus sin 2t, okay, plus 1 plus 1. So you can easily say the exponential positive system is unstable. Understand or not? So here the step responses of both the natural as well as the natural response component and the driven component, okay, both are having natural response component and driven response component. So 1 and 1, clear. So the natural response component is this one. Natural response component is, see, actually this consists of both. So this is a transient natural response or transient. Okay. So this is called driven response. Driven. Okay. Similarly, this portion is natural component, natural response component. So this one is driven response component in this case also. So driven response component on both cases is plus 1 only. But when t tends to infinity, if you apply t tends to infinity here, what happened? So the natural response do not decay to 0. Natural response do not decay to 0, right? So this component do not decay to 0. Clear? So there is a blow up. Okay. So also the exponential terms are positive. Exponential terms are positive. So the system is unstable. See, let's see the response of both system. So this is G1 of t, this is G2 of t. So G1 of C1 of t, this C2 of t. So both are not settled at 0. It is somewhere here. So the system is unstable. So these two systems are unstable. You can easily look into the exponential power. Okay, unstable. This is the example for unstable systems. Clear? So then, why you can ask me why are the exponential terms positive? Okay, why are the exponential terms positive? Okay, determined by the stable system poles. Why are the exponential terms are positive? That is determined by the system poles. For overdamped system, okay, for overdamped system, clear? For overdamped system, S1 equal to sigma 1 and S2 equal to sigma 2 on real poles. Okay. Then on step response, the step response of overdamped system is, say, R1 e to the power sigma 1t, sorry, positive, plus R2 e to the power sigma 2t plus 1. So this is natural response. This is driven response. Okay, driven response. So the step response is R1, R2. Sorry, you can have the constant here, depend on the poles. So that you can have it at 3. R3 is a constant. R3. Say, sorry. Can have a so R3. Clear? Any doubt? Please. Nobody is asking doubts. So similarly for underdamped case, okay, for underdamped case, what is the underdamped case? Zeta is less than 1. What is overdamped case? Zeta greater than 1, right? So remember this also now. So zeta under less than 1, okay, under damped case. So what are the poles condition? The poles are S1, 2 poles equal to sigma plus or minus J omega D. Okay, sigma omega D. So what is the step response? Its corresponding step response. Step response is C of t equal to R1 e to the power sigma t. Okay, sigma t cos omega dt plus R2 e to the power sigma t sin omega d t plus R3. So here this is natural response, transient response. This is driven response. Understand or not? So the sign of the exponential determined by the sigma value. So the sign of the exponential value determined by this sigma. Understand? So the real part of the system poles, if sigma less than 1, if sigma less than 0, okay, if sigma, let's see, if the sigma less than 0, it satisfies. So poles, okay, poles poles lies on the LHP, left half of the S plane. Okay. Then natural response is tends to 0 as t tends to infinity. The system is stable. System is stable. Understand? These are all conditions. If sigma is greater than 0, what are the case? So poles lie on the RHP, right off of the S plane. So the case natural response tends to infinity as t tends to infinity. Understand or not? So the system is unstable. System is unstable. Clear? Any doubt with this? So the purely imaginary poles. The case is when the purely imaginary poles. So purely imaginary poles. So what happened when purely imaginary poles? Clear? So LHP poles, okay, LHP poles corresponds to stable system, stable. So RHP poles, right out of the explained poles, corresponds to unstable system, unstable. This is the classification. It seems that imaginary axis is a boundary for stability. Okay, it is the truth, right? So this is the boundary for stability. Okay, so if poles lie on the imaginary axis, we already discussed. Okay, if the poles lie on the imaginary axis, that is marginally stable, conditionally stable, immediately stable. Okay, when the pole approaches to imaginary that imaginary axis, the stability decreases. Okay, either when the poles lie on the imaginary axis, that means the natural response either, for example, I will give a simple example. So step response of undamped system. So the case of undamped, okay, step. This is the simple example. Step response of undamped system. What is undamped system? Zeta equal to 0. So what is the step response C of t? Say for example, we consider 4 by s square plus 4. Say consider a transfer function g of s equal to 4 by s square plus 4. So for this, the root is plus or minus 2j. Sorry, S plus or minus 2j. Here the natural response of the system is cos minus cos 2t plus 1. So driven, this is a natural response. This is a driven response. Driven response. So the natural response either decays to 0 or tends to infinity. So the system is marginally stable. So that means it oscillates continuously, indefinitely oscillates. Okay, indefinitely oscillates. Understand? Okay. So the step response of undamped system gives marginally stability. So this is sustained oscillations. This is called sustained oscillation. Sustained oscillations. Clear? This is sustained oscillations. So then the driven response repeated imaginary axis, that also we discussed. So when the poles are the roots of the say, for example, let us consider a system, say G of S. This is repeated imaginary poles. So poles lie on the imaginary axis, also repeated. We already see. So for example, this is for example, I'm telling you. So G of S equal to 16 divided by S power 4 plus 8S square plus 16. This can be simplified as 16 divided by S square plus 4, the whole square. Okay. So the repeated poles on the imaginary axis S1, 2 equal to plus or minus J2. Then third and fourth, 3 and 4, poles 3 and 4 also plus or minus J2. So the step response of the system, is contains both natural and driven response. So C of t equal to minus cos 2t minus t into sin 2t plus 1. So this is our natural response. This is a driven response. Okay, this plus 1 is driven response, right? So what happened? So when the multiplying roots on lie on the imaginary axis, then the system is unstable. Remember, multiple identical poles on the imaginary axis implies an unstable system. Multiple identical poles on the imaginary axis implies to unstable. Okay, unstable system. So let me show you. This is the response, step response for undamped system. The poles, the repeated poles at the imaginary axis. Repeated identical poles, identical roots or poles on imaginary axis. This is step response of the repeated identical poles on imaginary axis. So the system is unstable. Understand, my dear student friends? Do you understand? Right, good. Okay. So far we have been discussed different cases of stability, depend on pole location, then based on impulse response, based on step response. Okay. So now we are going to see how to determine this stability. What are the techniques available? Is there any techniques to determine the stability of the control system? Okay. What are the various techniques are available for determining the control system, stability of the control system. Clear? So the techniques, various techniques, methods, okay, methods to determine the stability, or determine or calculate the stability, determine the stability. Okay, stability. So we know that all of you know the basic technique is Routh-Hurwitz. Okay, Routh-Hurwitz criterion. Okay, Routh-Hurwitz criterion is the very simple method, analytical method, Routh-Hurwitz criterion. Then root location, okay, based on root locus. Okay. Third technique is using the Bode plot. After drawing the Bode plot, we can easily estimate the stability conditions. So next, fourth is Nyquist plot. Then Nichols chart. Okay, Nichols chart. Nichols chart. So these are all the different techniques to determine, to calculate the stability. Okay, to estimate stability. So Nichols chart. So first, stability, actually the stability determined by pole locations, right? So first, poles are determined by the characteristic polynomial. Okay, basically stability, first we already see the stability determined by pole locations. First one is poles locations. So pole locations. Okay, and we can also determine from the characteristic polynomial. What is characteristic polynomial? So normally it is determined as a delta of S equal to 0. That is closed loop. This characteristic polynomial is nothing but 1 plus g of gh equal to 0. This is the closed loop characteristic polynomial. Okay. Factorizing the characteristic polynomial from the factors of the characteristic polynomial, we can tell the stability conditions. We can also tell from the factors, okay, whether the system is or not. Okay, from the characteristic equation also we can tell whether the system is stable. So from the factors of delta of S also we can tell whether stable or not. Okay, stable or not. Understand, my dear students, stable or not. So also we can determine from the array. We can form array based on the Routh-Hurwitz criterion. So based on the Routh-Hurwitz criterion also we can able to determine. So the first we see the stability from the delta of coefficient. Okay, so stability from the coefficients of characteristic polynomial delta of S coefficients, right? So stability from the coefficients. Let us consider a stable system has all poles in the left half of the S plane. So the closed loop transfer function is T of S, closed loop transfer function. We forget about the numerator. Okay, numerator of S. We don't concentrate on numerator because the stability is determined by the location of poles, roots of the denominator. That is characteristic polynomial of the denominator. So the stable system has S plus A1, S plus A2, etc. S plus AN. So all the denominator poles are having negative real roots. So all poles are minus. So the left all LHF poles are greater than 0, right? So result is that all coefficients are positive. You see, all the coefficients are positive. You see the condition for this system is stable. So on what basis is stable? Poles are negative. Okay. Also, uh, for all LHP poles, left-handed poles, this I equal to 1 to n. Okay, AI should be greater than 0. Okay, clear or not? For all I. So the result is all the coefficients are all the coefficients are positive, since this is a stable system. Okay, if any coefficient of delta F is negative, then there is at least one RH pole, right? The condition is condition for classification of a stable system based on stability from coefficient of delta of S, characteristic polynomial equation. Okay, if any coefficient, any one coefficient of delta of S is negative, then the system is unstable. Okay, that means one pole located on the RHS. So one pole on right half of plane. So the system is unstable. This is from the coefficient of the characteristic polynomial equation. Okay. If another point is, if any coefficient equal to 0, any one coefficient is 0, the system is either unstable or marginally stable. The system is either unstable or marginally stable. Okay, marginally stable. Clear, my dear students? Marginally stable. If all the coefficients are positive, then the system is, if all the coefficients are positive, the system may be stable or unstable. That we cannot determine from the characteristic equation. If all the coefficients are positive, the system may be stable. Okay, so these are all the observations by looking into the characteristic equation, that is delta of S. Okay, if any one coefficient is negative, strictly it is unstable. You can easily tell that it is unstable. If any one coefficient is 0, either system is unstable or marginally stable. If all the coefficients are positive, the system may be stable, Clear, the system may be stable or unstable, Okay, so then how to evaluate the system's stability? Then we go for detailed analyzing of the method. That method analyze that technique called Routh-Hurwitz criterion. Okay, so if all the roots of the characteristic equation, all the coefficients of the, so see, all the coefficients are positive, we may not able to tell directly whether the system is stable, but strictly you can tell if any one coefficient of del of S, the characteristic equation is negative, means you can strictly tell this is unstable. If any one coefficient is 0, you may not tell. Either you can tell either unstable or marginally stable. But if all the coefficients are positive, then we may not able to determine the stability. Okay, it may be stable. Okay, so it may be stable or unstable. Okay, the system may be stable or the system may be unstable. So we cannot determine from the positive coefficients. Clear? Understand or not? Okay. So to determine the whether stable or unstable, there is a technique called Routh-Hurwitz criterion. Simply RH stability criteria. Stability criteria, right? RH stability criterion, right? So what is RH stability? Routh-Hurwitz stability. Let us consider a closed loop system. Okay, not necessarily unity feedback, a closed loop system. Clear? Negative feedback control system or C. So this is G, this is H. G of S, H of S. Okay, understand? So what is T of S? So T of S equal to G divided by 1 plus GH. Okay, so the T of S equal to S plus 0, 1, S plus S Z2, etc. S plus Z2, S plus ZM divided by S plus P1, S plus P2, etc. S plus Pn. Okay. So numerator and denominator. Okay. So the denominator of the denominator of the closed loop system. This is closed loop transfer function T of S. Okay. The denominator 1 plus GH equal to 0 is called a characteristic equation, that is del of S. So the denominator is called characteristic equation or character equation polynomial, right? So characteristic equation equal to the closed loop system poles. Okay. So this roots of the, so see here that you don't forget the roots of the characteristic equation is equal to the closed loop poles of the system. Closed loop poles of the system. Okay. Closed loop poles of the system. What is the closed loop pole system condition? We already discussed. So for stability of the closed loop pole system, all the poles roots should be in the left half of the S plane. They should have negative real parts, causal and stable. Okay. So the condition for the closed loop poles, all the poles condition stability we already discussed. Once again we will remember that. So all poles means closed loop poles. Okay, all poles are roots. Okay, should lie on the lie on the left half of S plane. Left half of the S plane. Okay, that is they should have negative real parts of negative. They should have negative real parts. That is causal and stable. Okay, causal and stable. Understand, my dear student friends? Causal and stable. From RH criteria, without solving CE, we can say the number of right half of S-plane roots can be calculated without go for in-depth. So already I explained. Say if the roots of characteristic equation, we can say without doing the Routh-Hurwitz criterion, we can tell. Okay, how many number of roots lie on the right half of the S plane? How, if any coefficient is negative in the characteristic equation, then one pole lie on the right half of the S plane. Okay, understand or not? So let us see. Say, let us consider the characteristic equation in the polynomial format. So a0 s power 4 plus a1 s cube plus a2 s square plus a3 s plus a4 equal to 0. Okay. For stability, what is the condition? For stability, okay, all the coefficients already we discussed, right, should be in the same sign. All the coefficients, okay, all the coefficients means a0, a1, a2, a3, a4, all should be positive or all should be negative. Okay, either positive or negative. If you take a negative common, it becomes positive. Okay, so all the coefficient in the characteristic equation, okay, in the characteristic equation should be same sign. Okay, should be of same sign, either positive or negative, all negative. Clear? So either positive or negative. Okay, if there, say, there should not be missing of any coefficient. Okay, absence of any coefficient. There should not be any, should not be missing of. Missing means any coefficient is 0. Okay, missing should not be missing of any coefficients. Understand? In the characteristic equation. If these two conditions are necessary, okay, sorry, these two conditions are necessary and sufficient condition for stability in the Routh-Hurwitz criteria. These two conditions. If this condition is not satisfied, then we have to do the Routh-Hurwitz criterion analysis. Clear? Routh-Hurwitz criterion analysis. For this characteristic polynomial, let me write the RH table. Okay, Routh-Hurwitz table. RH table. Let us represent the values of RH table. So there are 4 s to the power 4. Understand? So s to the power 4, s cube, s square, s power 0 or 1. Okay. So a0, a2, even numbers. Okay, a0 starting from a0. Okay, reverse the characteristic equation. a0, a2, a4. Then a1, a3, put it 0 here. Okay. So now what is the this coefficient, s square coefficient? This thing we have to calculate. So okay, so how to calculate? Multiply these two. A1 minus a1 a2 minus, multiply these two. Okay, so a0 a3 divided by, you divide by this coefficient always, divided by a1. Okay, so what about this element? You keep the first these two elements as it is. You take this and this. Okay, it's a matrix. This and this matrix. What is going to happen? Now a1 a4. Okay, this element a1 a4 minus 0 into A naught, minus 0 into A naught, that is 0. A naught into 0 divided by the same coefficient A1. For the entire row, you will divide by this A1. Okay. So again, this is 0. You assign the new coefficient. This new coefficient as, say, this is A1 or A1A. Okay. A, capital A. This you write as a this you write as a, you see, this becomes always this into this 0, this cancel. So this becomes A4 only. So A4 repeated there, then 0. Clear? So 0. So what about this this row? This row is, you can take these two. Okay, this this A, this is A4. Okay, so this is what? A into A3. This you multiply these two, A into A3 minus A4 into A1. So A into A3 minus A4 into A1 divided by this coefficient for this entire row divided by this coefficient A. So you consider this value as B, here 0, here also 0. So understand how to estimate this? So it is a reverse phenomena of determinant, right? So the coefficient of S0 becomes this B into A4. So this B into A4 minus 0 into this A, right? So this element is B into A4 minus A into 0 divided by this coefficient B. So it becomes B1, A4. This becomes A4, 0, 0. So this is the method to fill in the Raut-Hurwitz table. Understand, my dear student friends? Okay. So from this, what are the observations we can make? Okay. What are the determinations about stability can be made from the Raut-Hurwitz stability, this criterion table? For stability, for stability, clear? Okay. First is first column elements. First column elements. What are the first column elements? So all the first column elements. Let us make in a different color. Then you can able to see. So all the element obtained from the first column of the Raut element. Understand? So the first column elements. First column elements. But my dear students, in the table, elements in the RH table must be the same sign. Okay, must be in the same sign. Must be in the same sign. All should be positive or all should be negative. Same sign. Same sign. Either positive or negative. Okay, same sign. There should not be any sign change. Okay, that is very, very important. Should not, no sign change. There should not be any sign change. Any sign change. My dear student friends, understand or not? There should not be any sign change. Okay. Also, suppose any one sign change in the first column of the Raut-Hurwitz. Any one sign change. What have to do? Okay. The number of sign change, the number of sign changes in the first column. We should consider only the first column equal to the number of poles lie on the right hand side of the S plane. The number of poles or roots lie on the right of the S plane. So it indicates that the system is unstable. Understand or not? This is the technique to fill the system. Understand? Clear or not? Okay. Consider any doubt with this? Okay. Clear? Let's see some examples related to stability. Okay. So examples and the analysis. Okay. Examples. Let's see the examples related to stability, Routh-Hurwitz criterion. Okay. Examples for Routh-Hurwitz criterion, RHC, Routh-Hurwitz criterion. Let us consider system. Okay. Let us consider the system. Okay. Let us consider system. So example 1. So consider the feedback system. So R of S, C of S. Okay. So the 50 is the gain and the 100, S plus 4, S plus 6, S plus 10. Okay. So let us find a solution. You consider the feedback system, then determine the stability. Question is determine the stability using Routh-Hurwitz criterion. Okay, that is the question. So what is the solution? First we have to find the characteristic equation. What is characteristic equation? Closed loop system, the denominator of the closed loop transfer function. Okay, so first to find the closed loop transfer function of the system. So what is the closed loop transfer function? So the T of S equal to, just multiply 50 into 100, this becomes 5000. Okay, so always you can easily tell this is 50,000. So these 5000 can be directly put. This is the easiest way to determine the closed loop transfer function. Then multiply these three factors and add, along with that you add 5000 in the denominator and add this also. Okay, so what is 4 into 6, 24, 24 into 10, 240. So denominator, the constant becomes 5240. So in the closed loop transfer function, you can easily determine, just multiply, or if suppose if it is not there, you can directly put 100 divided by 100 plus these three multiplication, 4 into 6 plus 10. Okay, that is to be added with the numerator coefficients. Okay, so S into, you can also add S into S square, S cube. So this is S cube plus, okay, so then multiply 4 into this 24, so 124 comes. So I will do, you also do manually. I determined the factors as 20 S square plus 124 S. So the denominator characteristic equation, the delta of S characteristic equation equal to S cube plus 20 S square plus 124 S plus 5240. Okay. So now let us form the row service. Say the first two rows. Okay. So the first two rows, you can take the common. You can take the common ratio also. You can reduce to common ratio also. So let's see. Let us form the first two rows. So first two rows, SQ, S square of the first two rows. So the put the values. So put the values here. 1 and 124. 1 and 124. Then 20 and 5240. You see here. So you can take this is 120. This becomes 250s, 220s are 40, 124 around 620s, remaining 40, say 262, right? So we can simplify by scaling an entire row by a factor. So they can simplify the scaling, okay? Scaling, you can scaling for the, that is for multiplication simplification, okay? Scaling entire row is possible, and entire row is possible. Row by a factor is possible. So you can do, because multiplying 20 into 124 or 5240 into some other value is very difficult to calculate, because no calculator is allowed inside the I think inside the gate center, right? And I think so. Huh? So now let us calculate the remaining factors. Okay, remaining factors. So you can do the remaining factors. Let us see. I'll put the remaining factors. So SQ, S square, S power 0, 1, 124. This is 1, 262. We scaled the values, right? So what is the value? 1 into 124 minus 262. It becomes minus 138. Similarly, this becomes a 0. This becomes 0, 0, minus 138, right? Then you take these two this row. So this into this, minus 138 into 262 minus 1 divided by 138. So 138. So what happened? 138 cancel. We will get 262. Very easy, right? So this is 0. Understand? So now look into the first column of the element. So first column of the row service element. So what is here? So important observations. First column contains one negative sign change. First column has one negative coefficient. First column has one negative, okay, negative coefficient. That means according to the criterion, how many sign changes are there? Okay, so if you travel from this direction, okay, if travel from this direction, so here positive to positive, no sign change. Here positive to negative, so one sign change. From negative to positive, one sign change. So there are two sign changes in the first column of the row array. So that means two sign changes. Okay, in the first column of the row array. So it leads to two poles lie on the right half of the plane, right half of the S plane. The system is unstable. Understand or not? The system is unstable. We can easily tell the answer, right? One more thing. So consider the system, consider the same previous system by replacing 50 by K. Consider the feedback system. Determine, question is determine the range of K for stable as well as unstable. Range of K for stability. Okay. So what is the solution? Let us see what is the solution for this. What is the solution for this? So again, solution. Let us compute the transfer function. Okay. So what is the closed loop transfer function? Closed loop transfer function CLTF T of S. Very simple. Same, but replacing the coefficients. So 100K divided by SQ plus 20S square plus 124S plus 100K. Okay, 100K. Understand or not? 100K. Okay. Sorry, small mistake. 100K plus 240. I missed in the previous sheet. Okay, 100K plus 240, right? So this is a closed loop transfer function. Okay. So the characteristic equation, that is del of S equal to SQ plus 20S square plus 124S plus 240 plus 100K equal to 0. Let us form the Routh array for this equation, characteristic equation. So Routh array, so SQ, S square, very simple, you can train up very fastly. Okay, S power 0, S to the power 0. So the first row is 124. Then second one, here actually it comes 240 plus 2 here actually 20. Then here 240 plus 100K. Okay, so you can take the nominal values. See, so this can be simplified as a ratio as in the previous case. Say scaling, we can scale the entire equation 120. So here I think 120, right? So 12 into 20, 12 plus 5K, simplified as 12 plus 5K. Okay, so what is the S power, S coefficient here? Okay, you multiply this and this minus of this and this. Okay, so what we will get? So we will be getting so my 112 minus 5K will be getting, right? This becomes 0. So then how to calculate this one? So this one, this into this, okay, this into this minus 0 into 1, 0, right? So it becomes divided by this. So this becomes the same 12 plus 5K. So 12 plus, sorry, 12 plus 5k. This minus 12 plus 5k. This 0. So now you observe the first column of the Raut array. What is the condition for stability? So since the k, if the first column of the Raut array, check the first column of the Raut array. What is the condition? All the elements in the first column of the Raut array should be positive. Okay. So first for stable, let us find the k value for stable condition. Okay, for stable. What is the condition for stable? So these two elements should be 0. So that means 112 minus 5k should be greater than 0. So what is the value of k? K should be less than 22.4. Similarly for unstable, so what is the unstable condition? The first column of minus 5k, this should be less than 0. That means k greater than 22.4. Okay. So what is this is the ranges of, okay. Also, if this is less than 0, when this is less than 0, so what happened? So the k, if you substitute k value here greater than this value, so one negative element occur. So for unstable, this becomes negative. So this element become negative. Two sign changes. So two poles in RH, right half of the plane. So this is the analysis. Understand or not? So these are all these standard methods to evaluate the stability using the Raut-Hurwitz criterion. Understand? Thank you. Okay. Now we can so far we have been discussed the different types of stability conditions. Now let us see the some special cases, right? Some special cases. What are the special cases in the Raut-Hurwitz criterion? Okay, there are two special cases arising in the Raut-Hurwitz criterion. So what are the two special cases in the Raut-Hurwitz? While doing the analysis in the Raut-Hurwitz criterion, there are two cases, special cases. First case is a only 10, okay? A0 only 10 in A0 only in the first column of the row, in the first column, okay, first column of the of a row. So any one, okay, any one 0 in the first column of the Raut-Hurwitz, right? Raut-Hurwitz criterion. Or second case, okay. So in this case, if any 0 in the system, divide. So what we have to do? Say first we see an entire row. First we see the special cases. Then we will find the solutions. Entire row of zeros. So an entire row contains zeros. An entire row contains zeros. So A0 only 10 in the first column. In the first column of a row. In the first column of a. So what is the solution for this? Solution for this is divide by 0. This is called divide by 0 problem when forming the next row. Okay. So this case is, this is nothing but divide by 0 when forming the next row, next row. This indicates presence of pair of. This indicates presence of pair of poles that are mirrored, okay, that are mirrored about the imaginary axis, okay. So these are all the two special cases arising while doing the okay. So the two special cases arising here is a zero only in the first column, a zero. Then an entire row of zeros, okay, entire rows are zeros, okay. So if a zero condition, if a zero appears in the first column, okay, appears in the first column, okay, column. So what I have to do if a zero appears in the first column? So first step is replace the zero, okay, the zero with some non-zero element, say plus or minus epsilon, okay, some epsilon. Then complete. Then after substituting that, complete the Routh table, okay, complete the Routh Hurwitz table, okay, as usual. Then take the limit as, these are the steps to be followed, okay. Take the limit as epsilon tends to 0. Then evaluate the sign of the first column, okay, sign of the first column entries, sign of the first column entries. So if a zero appears in the first column, replace zero with some non-zero element, so plus or minus, either plus or minus epsilon. Then complete the Routh-Hurwitz table as usual. Take the limit as epsilon tends to 0. Then evaluate the first column entries. Understand? So let's see one example. See, for example, the closed loop transfer function. Okay. The closed loop transfer function, T of S equal to. So let us consider this example, closed loop transfer function, say 10 divided by s power 5 plus 3 s power 4 plus 2 s cube plus 6 s square plus 6s plus 9. Okay. So the characteristic equation del of s equal to s to the power 5 plus 3 s power 4 plus 2 s cube plus 6 s square plus 6s plus 9 equal to 0. So let us form the Routh-Hurwitz table for this equation. Okay, so let us form so okay, s power 5, s power 4, then s cube. Okay, so first let us do the substitution. 1, 1, 2, 6. So 1, 2, 6. Okay, then the second s coefficient 3. Okay, 3, 6. 3, 6, 9. Okay, 3, 6, 9. So 3, 6, 9. So here we can take a factor, common factor. So what is the common factor? 1, 2 3s, 3 3s. Okay. Similarly, so the first row of the element 1 to 6, second 1 to 3, 1 to 3. Okay, 1 to 3. Let us calculate this element. So what is this element? Yes, 3. 1 into 2, 2 minus 2, 1 into 2 minus 2 into 1. So divided by 1. So what happened? This becomes 0. Okay, this becomes 0. So 2 into 6, 12 here. 2 into 6, 12. 3 into 2, 3 into 2, 6. So this element divided by 3. So sorry, 2 into 6, 12. 3 into 2, 6. 6 divided by 2, 3. So this element is 3. So this is 0. So since we are getting 1, 0 in the first column of the element, at this stage, we may not be able to continue further. Okay, we may not be able to proceed further with the stable values. So what we have to do? Replace the element 0. Okay, the 0 element. Which is 0 element? This element, 0 element with some non-zero epsilon. Then proceed. Now you put instead of 0, you substitute epsilon. Then proceed. So what? Then we proceed the table. So s square. Next is s square. Then s power 1. So then s power 0. Okay. So what is here? This stage 2 into e epsilon minus 3. Okay. So this element e becomes 2 epsilon minus 3 divided by epsilon. Okay. 2 epsilon minus 3 divided by epsilon. Understand or not? Right. Very good. Okay. So then this element becomes epsilon into 6. So epsilon into 6 minus 0 divided by epsilon. Okay, then this element becomes 6. 6 divided by 3, right? So sorry, this into this. So epsilon into 3. So this becomes 3, no? Sorry. Okay, epsilon into 6 divided by 3. So this is 3, right? So this element is 3. So epsilon into 3, this row over. So this row and this row, right? So 3, then 0. Understand? Then for this element, 2 epsilon minus e into 3, this into epsilon. So 3 epsilon minus 3 epsilon divided by this element. So what do you get? 1. Okay, that is 3 epsilon minus s power 1 is 3 epsilon minus 3 epsilon square. If you calculate, if you do this, you will get this. 2 epsilon minus 3. So this is the element value at this stage, S1. So this becomes 0. So this into this 0, then this also 0. So then what is the next element? S power 0. So this into 3 minus 0 into this divided by this. So this element becomes 3. Am I right? 3. So this is also 0. This is also 0. So this is the Routh-Hurwitz completion, table completion. So now we have to do take epsilon equal to 0. Substitute epsilon tends to 0 in this first row. Okay, the first column of the Routh array. As taking limit epsilon tends to 0 and looking the first column. Now, looking the first column, you see what is the first column. So here, this is epsilon. So what are the first column elements? So 1. Now I am replacing the first column element. You see, this is the new first column element. 1, 1, 0. Clear? 0. So here, if you put epsilon 0, this is also 0 minus epsilon, right? Minus epsilon. This is new element. So similarly, this also 0. S power 1 is also 0. So then 3. So 3. You see the green numbers. These are all the new elements of the Routh table after substituting epsilon is 0. So what do you infer from the new element formation after doing the manipulation? There are 2 sign changes. So 1 minus infinity is there. So there are 2 sign changes. 2 sign changes. Okay, then so the system is unstable. Understand or not? So this is the Routh table condition when one element becomes 0. One element is 0, replace with the element with the epsilon and proceed the calculation. Finally replace epsilon by 0. Okay, understand or not? So then what happen if rows of 0, the whole rows, that's case 2. Okay, whole row of zeros. What happened? Whole rows of zeros. Okay, so this presence of poles that are mirrored about the imaginary axis, I already indicated here. So the entire row 0 means the poles. Okay, so the indicates the presence of pair. Okay, presence of pair of poles that are mirrored about the imaginary axis. Pair of poles mirrored about the imaginary axis. Let us see what are the various mirror images for these cases. Okay. So this is one mirrored image about the imaginary axis. Then this also mirrored about the imaginary axis. Then here, then here, here, and here. Okay, so these are all the mirrored images. At the best, the system is this case is the system is marginally stable. Okay, marginally stable. So we can easily say marginally stable. So first case is at the best marginally system is marginally stable. Marginally stable. So use Routh-Hurwitz table to determine if it is unstable. Understand? So determine if it is unstable. So what we have to do if a rows of zeros called rows of zeros. So rows of zero, sorry, row of zeros, not rows, sorry, zeros, rows of zeros, row of zeros. So if an entire row of zeros appear in the Routh table, so we have to create step one. So if entire row of zeros appear in the Routh table, create auxiliary polynomial. Okay, create an auxiliary. Okay, auxiliary polynomial. Auxiliary polynomial from the row above the zero row. From the row of zeros, from the row above the row of zeros, simply skipping every other powers of s. Okay, then what we have to do, differentiate the auxiliary polynomial, with respect to s. Okay, with respect to s. Okay, then third step is replace the zero row with the coefficients of the resulting polynomial, that is differentiate. Okay, dp by ds, where p is the auxiliary polynomial. Then replace the zero row with the coefficients of p. Okay, this p is a resulting polynomial. Okay, resulting coefficient of resulting polynomial after differentiating resulting polynomial dp by ds, the coefficient of this polynomial row. Okay, dp by ds. Then complete the Routh table as usual. Do completion. Complete the Routh array. Okay, Routh array table as usual. Okay, as usual. So what is the next? Evaluate the sign changes. Okay, evaluate the sign of the first column. Okay, first column entries as usual. Understand or not? So let us do one example for this method, this thing. So consider this one example for row of zero. Say consider this for system. So let us solution. Okay, solution. So let's do solution. So let us form the Routh-Hurwitz table. S power 5. The characteristic equation is 0. So this is the del of s equal to s power 5. So 1, 11, 28, 28, s power 4, s cube, s square, s, s power 0. Okay. So 1, 11, 28, then 5, 23, then 12. So let us evaluate the third row. So what is this element? S cube. So 5 into 11, 55 minus 23 divided by 5. 23 divided by 5. So please do calculation, dear friends, student friends. Okay. So I'm getting 6.4. So 5 into 11 minus 23 into 1. So 6.4. Okay, 6.4. Then 5 into 28 minus 12. 5 into 28 minus 12. Do this, please, my dear students. Do it. Tell me the answer. What you are getting? Okay, 25, 25.6. 25.6. So this obviously 0. So can take common ratios. So 25, 25.6, 25.6 divided by 6.4. 20 by 3. I think okay. Okay, 4, 6 are 24. 4, 4 are right. Very good. So this is so this is 1 ratio. This becomes 4. So 1, 4, 0. Now let us do let us find the rows of s square. So s square will be getting 1 into 23, 1 into 23 minus 4 into 5. 23 minus 20 divided by 1. Okay, divided by 1. Okay, so that is 3. Okay, this element is 3. Then for this 1 into 12. 1 into 12 minus 0 divided by 1. Okay, so 12. So this becomes 12. Am I right? So 12, this is 0. So what is the next row? You see s square 3. Okay, this here also you can take a common value 1. This is 4 threes are right. 4 threes are this. So again we can calculate s coefficient s row, this row. So 1 into 4, 4 minus 4, 0. So s row 0. Then similarly 1 into 0, it's 0. This element also 0. This element also 0. Please listen, observe here the s coefficient elements. This row, okay. This row elements, see this row elements, full row, entire row are zeros. Entire row are zeros. If an entire row becomes 0, what we have to do? Consider the previous row elements. So this elements. So what is the polynomial for the previous thing? S square plus 4. So now create a polynomial. Okay. So the auxiliary polynomial. Auxiliary polynomial, right? Auxiliary polynomial. P equal to s square plus 4. Understand? So then differentiate. So find dp by ds. So 2s plus 0. Okay, 2s. That's all. Now replace s row with this coefficient. What is the coefficient s row? Only 2. Okay, you go back. So the s row, instead of 0, we can replace this coefficient 2. This is the new coefficient 2. Replace this with the auxiliary, resulting auxiliary element. Now continue. So what now if you continue from this stage, so what do you get? So 0 into 4, 2 into 4, okay, minus 0 into 1, 0, 2 into 4 divided by 2, 8 divided by 2. 8 divided by 2, this s power 0 is 4. So this element is 4, this 0, 0. Now, what are the first element, first column elements? Now, please tell the first column elements. What are the first column elements? The first column elements are 1, 5, then 1, then 1, here 2, okay, then 4. So what do you infer from this result? What do you infer from that? There is no sign changes. Inference, okay, inference from the first column. So no sign change, no sign changes, no sign changes. Okay, so what? No RHB poles, right hand poles. No poles lie on the right hand of the S plane. Okay, the rows of 0 indicates that, but even then, but the rows of 0, say rows of 0 indicates, what indicates? Indicates that the system is marginally stable. Marginally stable. Understand or not? So even there is no sign change, no RHP poles, the system is marginally stable. Clear? So let us once again see the discussion summary. So let's conclude with the summary. Okay, summary on stability analysis. What is the summary? First, so the coefficients. First one is the coefficients of delta of S have different signs. Different sign. Delta of S has have different signs. Different signs. Okay, the system is unstable. Unstable. Okay, then if some coefficients of if some coefficients of delta of S are 0, some coefficients of delta of 0, the system may be marginally stable. Marginally stable at the best. Okay, marginally stable. If the coefficients of delta of S characteristic equation have same sign, then system is either stable or unstable. So how to examine the stability? Go for Routh-Hartley, right? System either stable or unstable. So for detailed examination, we go for Routh-Hartley analysis. Okay. So to do a final examination, do Routh-Hurwitz criterion by forming Routh-Hurwitz table. Okay. If any one zero in the Routh-Hurwitz table, while analyzing, if any one zero in the Routh-Hurwitz table, then go for replacement of epsilon, this non-zero element. Then compute as usual. Finally, we will get the resulting column. From that, we can determine the number of sign changes, right? If all the rows, if this is for any one zero in a row, okay? This is row of all zeros, row of zeros. So for that, we have to form an auxiliary equation, okay? Auxiliary polynomial equation P. Then what we have to do? Differentiate with respect to S. Then substitute this auxiliary polynomial coefficients in the row, okay, by replacing zero rows, okay. Then do as usual, we will be getting the system stability conditions, either marginally stable or system stable, right? We can determine even though this thing, understand or not? So these are all the different summary. Okay, thank you very much for your observation. Please subscribe our channel. Happy learning. Have a new year. Okay, have a good new year. All the best.